Welcome, class, to the online portion and the trigonometric portion of this class. We're going to begin easy, and we're going to by looking at an acronym you've seen probably quite a few times before. If not the acronym, you've certainly seen the concept before, and that is SOHCAHTOA, right here. And that basically stands for sine is the opposite over hypotenuse, which we have here. And then we've got this guy over here, the cosine, which is the adjacent over hypotenuse. And then we finally have the tangent right here, going back to this guy here, which is simply means that the tangent is defined as the opposite over adjacent. Okay, and I'm sure we all understand this. Let's go ahead and look at this as a picture. If this is our angle theta, then this side would be the adjacent side. And this would be a 90-degree angle. That's what that symbol means. And then over here, this would be opposite side. And then that would make this side, the one that's not associated with the 90-degree angle, and in fact it is on the opposite side of the 90-degree angle. This would be the hypotenuse. Alright, and so theta, what does theta mean? Well, we kind of intuitively know that's got something to do with the angle. Well, theta, we're going to call that is a measure of the rotation. Alright, so if you take this side here, how far do you rotate it up? That's our angle theta. So it measures how much of a rotation it is. An angle describes how far a line is rotated. Okay. In degrees, one full rotation is 100. Oh my god, damn it. Okay, let me start that again. In degrees, one full rotation is 360 degrees, or 2 pi radians. Now, angles in a circle are measured from a reference angle. Or let's get that over. Reference line. All right. So, basically you have a circle. You've got a line right there. That's your reference line. And then you've got, how far is this being rotated around? Well, you measure how far it is from that reference line, and that is your angle right there. Alright, so let's go ahead and partially fill in this chart. We're going to fill in some of the fractions of turn, some of the reference points first, and then we'll fill in some of the details later. This one right here should be pretty obvious. This is 1/4 of a turn. And then this guy right here should be pretty clear that that is 1/2. Make sure you see, that's going to there. That guy is being rotated like that. Alright. And then over here, pretty clear that is 3/4 of a rotation. And then over here, this is simply 1 full rotation. Okay, so now how do we relate, what fraction of a turn it is to degrees and radians? Well, we simply use this knowledge up here that in degrees, 1 full rotation is 360 degrees or 2 pi radians. So essentially what we do is we take advantage of the fact that 1 rotation equals 360 degrees, which equals 2 pi radians. Okay, so now let's look at this one here. Let's convert this one into degrees and into radians. Here's how we do it. We simply say 1/4 of a rotation, right? Now, nothing peculiar there, and we're going to write this line here, and that line is going to mean multiplication in this case. And we're going to put the proper identity in the top and bottom that will make this rotation cancel out. So I'm going to put that in one rotation there are 360 degrees. And note what is going to happen here. Rotation is going to cancel out with rotation, and the reason we can do this is because one rotation is 360 degrees, so we're just multiplying by 1. And so we basically end up with 360 divided by 4, which is simply 90 degrees. And we'll go ahead and just write the little circle up top, which stands for degrees. And so when we go to fill this guy in, we write 90 degrees. Okay. And then likewise for 1/2 of a rotation. It's the exact same thing. Just draw your line like that. You know, I put the 4 down here on this one. I put the 2 up top. As long as you're kind of consistent in your notation, which one you do doesn't matter. And so we write 360 degrees over 1 rotation. Rotations cancel. The unit rotation cancels. And so we're left with 360 divided by 2, which is simply 180 degrees. Okay. And then we can perform the same thing for here and here. Let me just go ahead and fill it out for you. And so you get 270 degrees here and 360 degrees right here. Now let's look into how to convert from degrees into radians. Basically use the same setup. We'll go and take a look at this guy here. That's 90 degrees. So we'll write that out. 90 degrees. And we're going to go ahead and say in 180 degrees we've got pi radians. That's the conversion we're going to use, because if you notice, if you look up here, you have 360 and you have 2 pi. You divide both of these by 2, this guy becomes pi right here, and this guy becomes 180. So we have pi over 180. Alright, so now we simply do the math. We do not calculate pi, we just write pi off on the side. And so we've got pi times 90 over 180, which is simply 1/2. So we write it as pi over 2. And so that goes right there. Okay. And then likewise for 180, and we've got 180 degrees. Okay. And then 180 degrees we have pi radians. And of course 180 over 180 is 1, and so we end up with simply pi radians. And I forgot to write the unit here. It's not so important to write it when it's radians all the time, but you do want to keep track of your units. So degree to degree, degree to degree. All right? And so when you write this in, this is simply pi. Now I encourage you to do the math for these two. I'm going to go ahead and just fill them in for you right now. And you get 3 pi over 4 and 2 pi right here. Alright, so let's go ahead and flesh out some more of this table. So right here, you notice this is half of 1/4 of a rotation here, making this simply 1/8 of a rotation. Alright, very good. And then let's see, we go over to right here. Oh, come on, where'd it go? Are you freaking kidding me? Where the heck did it go? Okay, found it. And of course it's recording while I'm trying to find it. Okay, well hopefully I remember to edit that out. Alright, so this is 3/8 since we're in between 1/4 and a half. And this guy right here, you know, we're between a half and 3/4, making this simply 5/8. And this angle right here, we're halfway in between 3/4 of a rotation and 1 whole rotation, making this 7/8 of a rotation. Now, this little rotation in here, it's correlates to a special triangle that we're going to talk about later. This happens to be 1/12 of a rotation. All right, and then this little angle right here is simply 1/12 of an additional rotation after 1/8, making this simply 1/6. And if you note 1/12 plus 1/8, you will get 1/6. So we're just going to go ahead and fill in the rest of these rotations. Since they reference to the reference triangles that we're going to look at on the other side of this handout. This is 1/12 of a rotation. This guy right here is 1/6 of a rotation. This fraction of a turn here, that is 1/3. Here we've got 5/12, 7/12, and then here's a nice angle, 2/3, 5/6, and then 11/12. Okay, good. So we want to go ahead and convert all of these rotations into degrees and radians. One thing we start to notice for the radians already is that right here, the 1/4 of a rotation, well, that's pi over 2. 1/2 of a rotation, we've got pi. 3/4 of a rotation, we've got 3 pi over, I'm sorry, that should be 8/2 right there. And then here for 1 rotation, we have 2 pi radians. So kind of get a feel for the pattern going on. Here for 1/12, we end up with pi over 6. Note that 6 is half of 12. Here we've got 1/4 of rotation, pi over 2. 2 is half of 4. 2, and then we have a 1 underneath here, which, obviously 1 is half of 2. And then the 3/4 of a rotation, again, 2 is half of 4. So to convert to the radians, all we got to do is just take half of the bottom number there, and then we will have it. And there's a reason for that. It's because of our conversion. If you look over here, where we've got, here it is, 1 rotation equals 2 pi radians. Well, we're multiplying by 2 pi in order to convert into radians. So let's fill this out. 1 over 8, that ends up being pi over 4. All right. 1/3 rotation's a little bit more tricky, but you know, again, we're multiplying by 2 pi, right? So 2 pi over 3. All right. Here we've got 3 pi over 4. Here we've got 5 pi over 6. And just keep going down the line. 7 pi over 6. Here we've got. Now for the remainder of these, we have to convert from radians into degree, which is kind of the opposite of what we were doing down in this section here. In order to do that, let me go ahead and just we'll take this pi over 6 and we'll work it out here on the side. We have pi over 6 radians. We want that in degrees. Alright, so we simply use our conversion factor from radians to degrees. Make sure we have the right units in the right spot. Alright, like so. And so there are pi radians in 180 degrees. And so we can see that radians cancels with radians, and we get our pi's cancel as well. So it ends up being simply 180 divided by 6, or more simply 30 degrees. Fill that in here. And there we got it. Now I encourage you to practice calculating the degrees for each of these. I'm just going to go ahead and fill them all in for you real quick. So this one is 45 degrees. That is 330 degrees. Okay, so that's our table all filled out. Don't worry so much about memorizing the fractions of the turn. I do expect you to have the degrees down, and I definitely expect you to have the radians down. And the reason that I emphasize radians so much is that when you get to Cal 1, the radians become very important, and you really want to have these radian measures committed to memory. And we're going to go over these in the unit circle on the other side of the page, where they'll be a little bit easier to digest. So in this class, we will primarily work with radians. That does not mean that degrees are not important. Make sure you are comfortable working with them. Okay, so let's come over here to arc length. And so arc length is defined as r times theta. Or should I say is described by r times theta. What is arc length? It's simply the length of the circle along here. Like that would be, with the length of that circle, if you were walking along there, that would be your arc length. And this is your angle theta, and this is your radius. Okay, that's kind of the setup there. And so this is where theta is in radians. If you use theta in degrees and don't convert, you're going to get the wrong answer. And so let's take this definition and take a moment to look at the formal definition of radians. So radian is defined when the arc length is equal to the radius. And let's see what this does to the equation, right? If the arc length is the same as the radius, well then the radius would be r, right? And so just plugging it into this equation here, and that equals r times theta. Divide both sides by r, what do we get? We get that 1 radian is equal to theta, which fits our definition. All right. Now, most of us probably don't have a feel for how much of a rotation 1 radian is. So why don't we convert radians into degrees? Because we do probably all have a somewhat intuitive feeling for degrees. So let's go ahead and convert 1 radian that we have here into degrees. All right, so we've got pi radians here into 180 degrees. And so basically we're going to end up in radians to radians, left with degrees. So it's going to be 180 divided by pi, and when you run the numbers you will get, when you punch this number into the calculator, you will get 57.2957, and with a whole lot of decimal places. I should probably do the about equal to. So pretty close to 60 degrees is 1 radian. So it's not an insignificant rotation. All right, so let's take a look right here, this side here. We simply want to be able to relate different angles to each other. And so if we call this angle here alpha, well then that means that this other angle here is also alpha. And if we have another angle here that we call beta, then the angle over there, well, it's also beta. And note that right here, if you swing all along, you swing 180 degrees. So that would imply that alpha plus beta equals 180 degrees, or 2 pi radians, depending on which unit of measure you're using. All right, and also note the similarity between this angle and this angle. This line is parallel with this line, and we're working off the same line, so that means that this angle will be the same. All right, since this line is parallel to this line. And likewise, this angle will be the same as that one. And then we simply have the same scenario here. Okay. And we can kind of repeat this as we go on. If you note that this angle is also parallel with this line, and we're on the same line here, we can use the exact same logic to deduce this is alpha, and that is also alpha, and then keep going like this. And then again, we have a parallel line situation here. Simply fill it out. Like so. Okay. There's the front of the handout. Oh, not too far. Okay. Alright, so we have these two isosceles triangles. I'm going to zoom into one so we can kind of get a good look at this one. Alright, so for this isosceles triangle, we're going to let both sides be 1, and that angle will be 90. And so using Pythagorean's theorem, we have 1 squared plus 1 squared equals this side. We'll call it c for right now, equals c squared. Alright, so 1 squared is 1. Add the two together. We get 2 equals c squared. So what is c? It's simply the square root of 2. Note we're not taking the negative since it doesn't make sense for a length to be a negative number. So c is simply the square root of 2. So we want to know what is theta. And since it's an isosceles triangle, theta is the same in both cases. So how do we find our angle here? Well, simply go. This is an isosceles triangle, so these angles are the same here and here. So one thing about triangles is that the sum of all the angles is 180 degrees. Or, now that we're getting familiar with radians, that would be pi radians. And so we have 180 degrees equals theta plus theta, just do theta, plus 90 degrees, since that's our 90 degree angle there. Subtract 90 from both sides and we get 90 here. Divide both sides by 2 to find theta, and we find that theta simply is 45 degrees, which was one of our reference angles. And as we recall, 45 degrees is the same thing as pi over 4 radians. Okay, good. So what we want to find out now is what is the cosine and sine of 45 degrees. We're going to use this to fill in the unit circle below. So we say, okay, so cosine of pi over 4. Well, what is that? Well, cosine is simply the adjacent divided by the hypotenuse. 1 divided by the square root of 2. And now we don't want to keep a square root in the bottom, so we multiply top and bottom by the square root of 2. And when you do this, bottom becomes 2, since square root of 2 times square root of 2 is simply 2. And in the bottom, all we have is the square root of 2. Cool. Alright, now we're going to use this to find, now we're going to go ahead and find the sine of the same thing, of the same angle. Sine of pi over 4. So we're going to look at this angle. You could use this angle too. Result would be the same. So sine of pi over 4 is going to be the opposite over the hypotenuse. So opposite is 1, just like the adjacent. It's going to be over the square root of 2, which, as we already saw, will end up being the square root of 2 over 2. Okay, cool. All right. These can become very important down below, so keep these in mind. Put a pin in it for now. We're going to look at the other isosceles triangle. It's not an isosceles triangle. We're going to look at the other triangle, and we're going to go ahead and figure this one out. This is also going to be a similar triangle that is referenced to quite often. So for this triangle, we're going to make each side is equal to 1. This is an equilateral triangle. And note this line coming down and bisecting the line down here. Well, so this cuts it in half. So now this is 1/2 and 1/2. Now another thing about the equilateral triangle is that every angle is the same, right? So 180 equals 3 times theta, right? Because each angle is the same. 180 equals theta plus theta plus theta. So to find each individual angle, we simply divide both sides by 3, and we end up with 60 degrees. All right, and we know from the table on the other side that 60 degrees is the same thing as pi over 3. So let's fill this in. This would be pi over 3, pi over 3. And so note that this line again, this is cutting this angle in half. So let's go ahead and put this here. And what is half of pi over 3? Well, that's going to be pi over 6, which is the same thing as 30 degrees. Okay, so now we have everything we need to find the cosine and sine of both pi over 3 and pi over 6. All right, so cosine pi over 6. And so again, we're just going to be focusing on this triangle right here. So cosine pi over 6. So adjacent is going to be this side right here. Looks like we haven't found the length of that side yet. Let's go ahead and do that now. We'll call this side A. So we have 1 squared. 1 squared equals 1/2 squared plus a squared. Right? So let's go ahead and work this through. 1 squared is 1. That's 1/4. And that's still a squared. Sorry about that. I'm going to erase. There it goes. Alright, subtract the 1/4 from both sides. And we get 3/4 equals a squared. Take the square root. And we find that a equals the square root of 3 divided by 2. There we go. All right, now we can find cosine of pi over 6. So this equals the adjacent side, which is root 3 over 2, and the hypotenuse is 1. So the answer is simply root 3 over 2. And then for sine of pi over 6, and this is the opposite, so it's 1/2 divided by 1, so it's simply 1/2. Okay. So that's it. We got cosine of pi over 6 and sine of pi over 6. Now let's look at pi over 3. So the cosine of pi over 3 equals, we have adjacent, which is 1/2, and they'll be divided by 1. It's fine. And then the sine of pi over 3, well, that's the opposite over the hypotenuse, so it's going to be root 3 over 2 divided by 1. Let's just leave it off, and there we go. So kind of look at this one and these guys and these guys. Note how the values are the same, but they're flipped between the cosine and the sine. All right, so let's take a look at the unit circle. Basically, I'm just going to fill this table in with all the values that we've found already here for you in a second, but before I do that, let's kind of take a look at what's going on, make sure we understand this unit circle. First, note this 30-degree mark. You can come straight to here. It's going to come straight down and across. Now we're going to place an x and y axis like so. So here's our x-axis, there's the y-axis. So note that the origin of our coordinate system correlates with the origin of our circle. And so we're going to be finding the x and y coordinates of each of these points here. Note this triangle that I've drawn out here. Note this is a 90-degree triangle with an angle here of 30 degrees. Well, we already know that this angle of 30 degrees is pi over 6 radians. And we already worked through everything here because the radius is going to be 1, right? Radius is 1. And so pi over 6, it's a very similar setup to this triangle here. And so all of our x and y values are going to be, what is the x? All of our x and y values are going to equal the cosine of the angle we're looking at. There and there. And so when you calculate this through, or when you just look up here, you got square root of 3 over 2, and then 1/2. And there you go, that's it. That is the coordinates of this spot right there. Okay, I'm going to go ahead and fill the rest of this out for you, and I'll go through a couple of memorization tricks to help us remember the radians. And then finally 0 or 2 pi rotations. Okay, so we'll go back to the x and y coordinates for each of these in a second. You're going to have to remember all the angles in the first quadrant right here. Just remember pi over 6 is going to be less than pi over 3. So it goes pi over 6, pi over 4, pi over 3, then pi over 2. Notice this angle right here correlates with this angle here, so it has the same number in the denominator. It has the same number in the denominator. And so you notice this quadrant right here, each of these individual angles corresponds to the angles in the first quadrant. Like this guy corresponds with this one. This guy's pi over 3, this one's 2 pi over 3. Here we have a pi over 4, here's 3 pi over 4. You notice that the number up top is 1 less than the number in the bottom. And of course here we've got pi radians. Now over here, now these also correlate with all the same angles, 6, 4, and 3, like so. But this time it's 1 more. So plus 1 here, and here it's 1 less. So 1 more than 6, that's 7. 1 more than 4, that's 5, and so on and so forth, even down to here. 1 more than 3, well, that's 2. Now for this last quadrant, a quick way to get them, we have the same setup here, 6, 4, 3. But note that if you double the number and then take 1 away, then you will get the number up top. 2 times 3 is 6, take 1 away is 5. 2 times 4 is 8, take 1 away is 7. 2 times 6 is 12, take 1 away, you get 11. Now let's finish off the cosine and sine for each of the angle. That is the x and y coordinates on the unit circle. So we look right here, pi over 4. What was the cosine and sine of pi over 4? Well, it was root 2 over 2 for both cases. And then for pi over 3, we need to know the x and y coordinates for the point. And so that's going to correlate again with cosine and sine of pi over 3. And so we already calculate that to be 1/2 and root 3 over 2. All right, kind of note how this one is flip-flopped with this guy right here. And then up top here, well, that's going to be the point x is 0, y is 1. Since it's right on the y-axis and the radius is 1, directly up. Alright, so we've got the x and y coordinates for everything in the first quadrant. Note that out here in the second quadrant, all the x values are going to be negative and all the y values will be positive. So we're going to fill in all the x and y coordinates, noting that they are going to correlate with these guys over here. But each x coordinate is going to have a negative sign in front of it. And then -1 and 0. Alright, all correlate. Now we come down here into the third quadrant, finding all the x and y coordinates. Note that in the third quadrant, all the x values are negative, and all the y values are also negative. And so, we get the following result. We just copy everything down from the first quadrant, but everything will have a negative sign in front. Like so, and then down here, of course, straight down by 1, and our y coordinate is 0. Now we enter the fourth quadrant, and in the fourth quadrant, all the x values are positive, and all the y values are negative. So we're going to repeat everything from the first quadrant, keep all the x's the same, but all the y values will have a negative sign in front, like so. And so here it is, here we have it. That is the unit circle in its entirety, and this concludes the handout. And so let's review. We started off talking about SOHCAHTOA, the right triangles between cosine, sine, and tan. And then we talked about radians and degrees and some special angles on a circle down here. We talked about how to convert between rotations, degrees, and radians. And the conversion factor is 1 rotation equals 360 degrees equals 2 pi radians. Alright, so we talked about some complementary and opposite angles here. And then we also talked about arc length and how we can use that to verify the definition of 1 radian, and we found that 1 radian was about equal to 57.2957 degrees. Here we used 2 special triangles to find the cosine and sine of some special angles, namely the angles pi over 4, pi over 3, and pi over 6. We use these to fill in our unit circle right here, all the x and y values. Now this unit circle is something that you should commit to memory before you get to Cal 1. If we are able to meet together one more time, we will have a test where we verify that we can memorize this. But if not, you would do yourself a big favor to committing this unit circle to memory. Okay, have a great day, and I hope this is going well, and you may email me if you have any questions. Have a great day.